So I'm going to start with this book proper, and but if you just follow it directly, you might get kind of scared off by the mess of technicalities that you will see there. So I want to kind of first tell you in advance what we'll be trying to prove, and then we'll go into all the details that's involved there. So first, let me just give you a quick idea by looking at the finite dimensional case. Right? So, see what the basic fact is the following thing. Namely, on how should I say this? Okay, so let me motivate it by discussing the finite dimensional case first. Okay, so suppose H is n dimensional. So might as well think of H as Cn. Right? And then so B of H can be identified with identify this with MNC, where operators is thought of as multiplication by matrices. Okay, so the basic fact is the following thing. So if you look at, see what will be important is the space of continuous linear functions on this space. So let us see what B of H star is in this case. Right? See, B of H is the collection of all n matrices. So it has a norm. See, on B of H, on Mn. So what is the norm on Mn? If you take a matrix like this, what is the norm of such a matrix? So you must think of this matrix as a linear operator on H, on Cn. And the norm is going to be the operator norm, right? So how do you compute the operator norm? So this is operator norm. So to give you an idea of what's going on, I want to say that let's look at the simplest case where this matrix is diagonal. Suppose this is diagonal. So what is the norm of this matrix? Lambda 1, lambda n. What is the operator norm of this matrix? So this is going to send the vector x1, x2, xn to lambda 1, x1, lambda n, xn. And then you must take the L2 norm and then take the soup, and so what is the bound that you will get? So you will get maximum of mod lambda n, or I just call this I think of lambda as an n-tuple, and then it is the L infinity norm, right? So what is the dual of L infinity? I mean, if you put the infinity norm on Cn, so if I want to take the dual space, the dual space of an n-dimensional space is again going to be n-dimensional. So MNC star can be identified with MNC as a vector space. because it's finite dimensional. But what is the norm now? So at least for a matrix, for a diagonal matrix, the norm of diagonal lambda what do you think it will be? If you just think of, rather than look at all of MNC, we just look at the diagonal matrices. So acting on diagonal matrices by just multiplying it, basically taking in a product. So what is the norm that you will have for this vector as a linear functional on Cn? See, so rather than looking at matrices, I just look at Cn. I just look at the diagonal part. So I'm saying, what is Cn star? What is the norm in Cn star? Cn star as a vector space. So we'll go back one step. What is Cn star as a vector space? This Cn as vector space. And what was the norm of some, let me call it phi rather than lambda. So the phi is what? Phi 1, phi n. How does phi 1, phi act on a lambda? It acts as summation phi I lambda I. And what will be the norm of that as a linear function? Don't look at my face, just scribble on the paper and see what it will be. What is the norm of in Cn star?
Again, we can treat this as an operator and we can
But how do I compute that now? If I take the vector 1, 2, 3, 4 in C4, what is its norm as a linear functional? What is this? This is going to be maximum or soup, if you wish, of summation phi I lambda I over norm lambda infinity equal to 1. Okay? So what is the obvious norm that you will get? So you want to write this as 1 other than equal to constant times. If you want to, what is the obvious constant? If I take infinity norm lambda to be 1, what is the obvious upper bound for this quantity? Absolute value of summation phi I lambda I. Mod lambda I less than equal to 1 for all I. Yeah, so the maximal natural candidate will be the L1 now. It will be summation mod phi I, that will be the norm. Right? Okay, and so basically the trace of this L1 L infinity norms are kind of dual. That's what this says, right? So there is a vestige of that in infinite dimensions, or even in the matrix case. In fact, computing the norm of, if we take matrix Xij or Phi and think of that as a linear functional on NBN matrices. What will how will Mn as I said this is MNC as a vector space. So I take a Phi matrix. How will that act on an Xij matrix? It will act by summation mod Phi Xij, right? So there is no difference between Cn and Cn square. But except the norm is not the infinity norm for in n squared. So you must be a little careful, and so the facts are these. So how do I say this? Okay, so rather than telling you the answer in finite dimensions, we'll go to the infinite dimensions straight away. But I'll just tell you what the basic fact is that we'll be trying to prove. So what is true is that in fact B of H as in the finite dimensional case, B of H is like MNC. MNC is actually it is a dual space of MNC with a different norm. See, in finite dimensions, now if you take the dual of, if you have a finite dimensional space X and you take X star, then the dual of X star is X again. So MNC can be thought of as the dual of MNC, where this MNC is given this funny norm, the linear functional norm. Right? So what is true is that it is true even in the infinite dimensional case, that in fact it turns out that this is a dual space. That means E, you can write this as there exists a Banach space, which I will denote by B of H lower star, such that B of H is equal to B of H lower star upper star. It is a dual of some space, so that space I like to think of as a pre-dual. Okay. And what is that pre-dual? So it will turn out that in fact see the whole problem is with infinite dimensions. See in Mn see if things have okay, so let me see what the how do I say it? See, MNC is actually a dual space, I'm saying, right, of MNC with some other norm, which means on MNC there will be a weak star topology. There is a topology for which convergence means convergence against all things in the previous thing. So what does that mean? That means, so what is the pairing of MNC? So, how shall I call it? See, the pairing of xij with phi ij in the matrix case now. So let's go back to infinite dimensions. This is going to be summation phi ij xij. Right? Which can actually be thought of okay, I guess see what I'm trying to say is that in finite dimensions at least, the weak star topology is nothing but what we call the weak operator topology. So I want you to see why that is true. See, what does it mean to say that phi xi converges to x in the weak star topology? What does that mean? That should mean that this is equal to saying that xi phi converges to x phi for all phi. Now I want to go back to think of these as operators, right? So for that what I want to say is that really what is xij saying this? Okay, see what I'm kind of struggling to say is the following. If I take a phi in Mn and something in Mn is viewed as an operator on Cn, right? So I can think of this phi as an operator acting on xi. So what is this? So any xi in your infinite dimension, so that you can write this as some xi xi or ci xi, where xi is an orthonormal basis. Right? So this looks like summation Ci phi xi. So any phi looks like no, apply it to this phi. We're saying the wrong thing. So, okay, okay, let me start again. See, MNC has a natural basis, which is the matrix is Eij. The matrix with 1 in the Ij spot, 0 elsewhere. Right? So, weak-star convergence is equivalent to saying that so X alpha converges to X weak star is equivalent to saying that X alpha Eij converges to X Eij for all Ij. Right? Because everything is a finite linear combination of Eij's. If you have this for all Eij's, you will have this for all linear combinations of Eij's, and hence for everything in Mn. Okay, so, but what does Eij look like? So this is just the Ij entry of X alpha, right? Entry wise you must have convergence. So this I can think of as X alpha Xij in a product Xi, where this is the standard orthonormal basis for Cn. Right? Right. So weak star convergence here corresponds to exactly I'm saying, so this happens if and only if X alpha converges to X in weak operator topology. Because that's what we've seen. If X alpha converges to X in weak operator topology, then you check it on the basis vectors, then you'll see that you have exactly that. Okay, so so what will be true is that okay, so what we will head towards proving, well, we eventually get there, the following. See, in B of H star, that is, if I want to look at linear functions on B of H, I have the natural mappings, let me call that omega xi eta, which is this mapping, where xi and eta in for xi eta in H. I hope what I'm saying is clear. I fix a xi eta in H. I look at a scalar valued function defined on B of H. You give me an x, I will compute x xi eta. I will get a number. That is clearly a linear function. So what is clear is that all these omega xi eta, they are all continuous. the linear functions on B of H which are continuous with this weak operator topology. By definition, the weak operator topology is defined by such linear functions, by the semi-norms given by such linear functions. And what we'll find is that this B of H, okay, so now let me get to, so what will, so we'll eventually prove that B of H star is the closed span of all omega psi eta closure in B of H star. That is, we will prove that B of H has a pre-dual which is identifiable with the closure of the linear span of these weak operator topology continuous functions. Okay, so this, so he first discussed these things in some generality because you don't need to clutter the notation with V of H, it's just confusing unnecessarily. We'll bring this in later, so okay, so we will now discuss the following situation. We'll be looking at, so E will be a vector space which you will think of as B of H as B of H. Right? You will think of this as B of H. And we'll be looking at various linear functions on this and topologies on this and so on. Okay. So, so the first thing to note is that, so actually I should say a non-vector space. Later it will actually be there will be a Banach space actually. Okay. Okay. And so we'll typically be interested in some collection subset of E star. E star is all bounded linear functions on E. Right? For each F in phi in F, we have a semi-norm, right? P phi of x equal to mod phi x. And this is clearly a semi-norm. And one looks at the topology induced by this family of semi-norms as phi ranges over F. Okay. So rotation is one writes sigma E F to be the topology on E, I should say vector space topology on E induced by all the semi-norms P phi, phi in F. Now this unnecessary tongue twister, what one is really saying, see what how does one define such a topology? In terms of which nets converge in this topology. And x alpha will converge to x precisely when phi of x alpha minus x goes to 0. But if you look at what phi of x alpha minus x is, here this phi is actually a linear function. So p phi of x alpha minus x goes to 0, the same as saying phi of x alpha goes to phi of x. Right? So convergence in this topology is equivalent to phi x alpha converges to phi x for all phi in F. See, you've seen examples of this kind of topology. For example, if E was itself a dual space, and then in E upper star, if E was the dual space of some G, then G sits inside E upper star. And so example, if E is itself a dual space, suppose E equals some E lower star star, then E lower star sits inside E upper star naturally. In finite dimensional or more generally in reflexive spaces, the two will be the same. Right? And you've already seen this in basic functional analysis courses, that if you look at sigma E lower star, you've seen this topology before. Right? Well, what do you call that? Huh? Yeah, this is called the weak star topology. Sigma E upper star is the weak topology on E. Sigma E lower star is the weak star topology. Right? Okay. So okay, so what we will do is to show that if we take this F to be this linear span, then sigma EF, and E is B of H, and if F is the span of all omega xi eta, then sigma EF is nothing but the weak operator topology. So what we will prove, okay, so let me explain. So when another example, when E equals B of H, and if I take F equal to the span of all omega xi eta in H, so in all this I have said that F is actually a vector space. I take a vector subspace of E upper star when I talk about sigma of EF. Okay, then what we will show is that, so this F is certainly contained in E star. and sigma of EF, you already observed, is nothing but the weak operator topology. And what we will show is that F closure, see F is a subspace of a Banach space. So if you take F closure, those which are norm limits of such finite linear combinations of such things, those will be exactly the pre-dual of F of E. So we will prove. That is that the E is identifiable as the dual space of this F closure, and we will be interested in the weak star topology on E. That is the sigma E F bar topology will then be that weak star topology, and is sometimes called the sigma weak topology or weak star, or some other people call it the ultra weak topology. They're all the same. So in a nutshell, I tell you what a one-Neumann algebra is, since that's what we're going to supposedly be talking about this course, is they are we've talked about C-star algebras. Actually, I defined a C-star algebra as a norm-closed subalgebra of B. What was there? Is there anyone there? Yeah. So I defined a C-star algebra as a norm-closed subalgebra of B of H. But in fact, there is an abstract definition of C-star algebras. So I talked about the C-star algebra generated by a set. So I defined it as, so there is one, I'll call it a concrete definition. It's just this a norm closed star subalgebra of B of H. Okay, this is a concrete definition of a C-star algebra. It ties the thing down to one Hilbert space. But there is an abstract definition. There is an abstract definition, which is that it is a Banach algebra that is, it is a Banach algebra with a star operation defined on it, and as usual, when you impose several structures, they must be interrelated by in some manner for it to be useful. So such that norm of x star x equals norm of x squared for all x in the algebra, Banach's algebra A for all epsilon. So now I tell you how to compute norms in MNC as operators. You know how to compute the norm of a diagonal matrix, right? It is the infinity norm. Now this says that if you give me any x in MNC, its norm is the square root of norm of x star x. But x star x is a self-adjoint operator. The spectral theorem tells you that can be diagonalized. So once you compute the eigenvalues of x star x, you can compute the norm of x, and thereby you have the norm of x for a general x. Even in a general C-star algebra, not just finite dimensions, you know the norm of, if you take a self-adjoint operator in a C-star algebra. Okay, so let me back up. So one proves that you will prove that these two, and there is a theorem which says that these two notions are really the same. Meaning, if you have one such abstract C-star algebra, see, in the category of C-star algebras, there is a natural notion of morphism. The morphisms are star algebra homomorphisms. So one will prove that there is, there is an isomorphism in the category of C-star algebras between such an abstract C-star algebra and a concrete C-star algebra. That means you have an isomorphism pi, that means I'm mapping pi from this A to a B of H. Usually one calls those things representations of A. One has a representation of this abstract C-star algebra which is one-to-one. Okay, and similarly when one talks of von Neumann algebras, there is a concrete definition, which is as a WOT closed star subalgebra of B of H. Actually, this is equivalent to a sigma weakly closed star subalgebra of B of H. The sigma weak I just defined for you. We haven't yet proved that theorem about B of H lower star. But once you have that notion and then this notion are the same. So this is for some H, you can represent it like this. The abstract definition is that it is a C-star algebra M such that there exists M lower star. That means it is a dual space as a Banach space. There is some Banach space M star such that M is naturally identifiable with M lower star star. See, the good thing about this, knowing this there exist p-duals, is that you're approved to learn this one fundamental fact about the weak star topology. Right? What is the one theorem you've learned about a weak star topology in a Banach space? Not in a Banach space, in a dual space? Huh? That the unit body is compact. Once you have compactness, the lot of things can become easy. So, So where did I? Yeah. So we want the category of one-Neumann algebra rather than C-star algebras. They are going to be C-star algebras which admit pre-duals like this, and those are the objects of the category. What are the morphisms of the category? There will be star algebra homomorphisms, which are continuous when you give this weak star topology in domain and range. Right? And here, if a sigma weakly closed subset of B of H, so there is a general nonsense theorem again in functional analysis. We will say that such a thing also has a pre-dual. Namely, what I am saying is, if I have E and in a dual space, if I have a weak star closed subspace, then that will also have a pre-dual. So I am saying, so this will mean that any concrete one-Neumann algebra is also an abstract one-Neumann algebra. And so it will make sense to say that there is an isomorphism in the category of one-Neumann algebras between any abstract one-Neumann algebra and a concrete one. Right? So this way we are heading, and it is because even in C-star algebra theory, the interest is in understanding all possible representations of the C-star algebra. Even for a commutative C-star algebra, the interest is in understanding all normal operators. That is what representation of a C sigma looks like, where sigma is compact in C. Or you can have more general compact Hausdorff spaces, but anyway. So representations of C-star algebra is important, and that is why it is good to have a C-star algebra as an abstract thing and not tied down to one fixed Hilbert space. A representation means if you give me different mu's, I can represent this Cx on L2 mu for different mu's. I don't have to, if I will lose that freedom once I say no, this Cx is a subset of the B of L2 mu for some mu. So that is why the abstract formulation is important when you want to study different modules of this algebra, the different representations of this algebra. Okay, so this is why this pre-dual thing is important, and so now let's get down with the theorem that I promised before. So we will now get back to basics now. Okay, so we'll start with this simple lemma. So it says suppose E is a vector space. First, it will always be a Banach space, but for this lemma it can be just a vector space. And suppose phi is a linear function. Okay, so I might as well use this language. I'll use the word form for functional. Linear form means linear functional. Linear form on E. And suppose P1, Pn are semi-norms on E. such that mod phi x is less than or equal to summation pkx. If you, the reason this kind of thing is natural is when you look at sigma EF, where F is a vector space of linear functionals on F, and then the seminorm is given by those P phis where phi comes from that F, then things which are continuous with respect to sigma phi F will be those which satisfy this kind of boundedness relation. That is what continuity at zero will mean. That is what it will mean to say that phi to say it is continuous at zero will mean that there must be some kind of boundedness condition that will translate to an inequality like this. That there exists P1, Pn coming from the F will satisfy this. So if you have such a thing, then there exists again linear forms phi such that phi equal to summation phi and mod phi less than or equal to pi for all. You're just splitting the thing up according to those pieces. Okay, so how does the proof go? The proof is not hard. So you look at e power n, and on e power n we'll define one seminorm p. I think p of x1 xn equal to summation pi xi. So it is clear that this is a seminorm. This is a seminorm on e to the n. Okay. So for this we will use the Hahn-Banach theorem in the seminorm formulation. So that you can find in my book actually, the Hahn-Banach separation theorem, I have called it. So we say that if you have a linear functional which is bounded by a seminorm on a subspace, you can extend that to a linear functional on the whole space which is bounded by the same seminorm. You have a seminorm defined on a big space and a linear functional defined on a subspace which is majorized by that seminorm on that subspace. You can extend to a linear function on the whole space, still so majorized. Okay. Now in En, and there is another. In En, you look at the diagram. X3. This is a subspace of En, because you can add two such things, it's going to be the same thing. The way addition is defined in the Cartesian product. And on D, let us define the function form phi naught on D. Defined by phi naught of xxx equals phi of x. We start with the phi defined on E. I think of that as actually the E can be identified with D. E is isomorphic to D. So I transport that phi to D and call that phi naught. And what is clear is that mod phi naught is less than or equal to P on D. By construction, that is what is true. So the Hahn-Banach extension will tell you that Hahn-Banach will tell you that there exists phi, a form on En, a linear form, such that phi extends phi naught and phi is dominated by P. Okay, so what was phi? Phi, I wanted to write phi as summation phi I. Now phi is defined on En now, right? So I define phi I of x. So this for x in E equal to phi of all zeros except in the ith place where there is a 0, where there is an x.
There is this phi on En, but phi has been given.
Huh?
Phi is fixed. Some phi dash.
Sorry, phi twiddle. Sorry, yeah. Phi was the given for. And now it is clear that if you get phi of x, what is phi of x? Phi of x is by definition phi tilde of xxx. But this xxx is the sum of n things which are of this kind with only one coordinate non-zero. And you can see that this is equal to summation phi ix. And phi ix is actually phi tilde of somebody, right? Phi tilde of and so absolute phi x is less than or equal to P of this fellow, which is Pi of x. So we have this. Okay. So E now is a Banach space. And F contained in E star, a vector subspace, just linear subspace, needn't be closed to anything. And phi will denote a linear form on E. Okay, so then phi is sigma E F continuous, if and only if phi is in F. See, this was the smallest topology where all these phis were continuous. All these phi in F were continuous, and those can be the only linear forms which are continuous. Okay, and this is the crucial one. Phi is so I'll write E1 for the ball of E. Unit ball of E. Everything of norm less than or equal to 1 is continuous, is sigma EF continuous, your linear form depends on all of E. Its restriction to its restriction to the unit ball is continuous in this topology precisely when phi is in F closure. So as a corollary, it will follow that, so sigma EF phi is sigma EF continuous on E1 if and only if phi is sigma E F bar continuous. I'm just using the previous thing for F bar. Then the two topologies agree on the unit ball, is what this says. Okay, there are two other parts to this. We'll state that later. Let us try to prove these two things today. The other two are fairly easy consequences of this. Okay. So, this is clear. And if phi is in F, then it's certainly sigma EF continuous. Because topology here means every phi must be continuous. So conversely, because this topology is given by those family of semi-norms given by F, so continuity is equivalent to being bounded with respect to a finite family of those semi-norms, which means if phi is sigma EF continuous, it will follow that there exists, let's say, psi 1, psi n, such that mod phi less than or equal to summation psi a, mod psi a. That is, this is the p psi a. But then what does the lemma that we just proved tell us? That tells us that I can write phi as, there exists phi 1, phi n. Now these are in F. By definition, right? There exists phi 1, phi n, they are just linear forms, such that phi equal to summation phi I and mod phi I less than or equal to mod psi I for all n. Now I ask you, suppose I have two linear functions phi and psi. So then mod phi is less than or equal to mod psi. When can that happen? So I want to say that for linear forms, phi and psi are dependent, linearly dependent. That means they're multiples of one another. See, this will show that the kernel of psi is contained in the kernel of phi. Right? But however, once you have a linear form, its kernel has codimension 1. Right? It has the whole space of the complex numbers. The kernel, if I take any vector not in the kernel, that together with the kernel will span the whole space. And the function will be completely determined by what it does on that one vector. So if we take one vector, okay, if psi is 0, then it is clear, they are both 0. If psi is not 0, you take a vector which is not in the kernel of psi. And then both phi and psi are determined by what they do on that one vector. The whole space is the span of that one vector and the kernel. On the kernel there is 0. So So what am I saying? I'm saying that if C of some x is non-zero, then I claim that phi must be equal to okay, so let's normalize so that C of 1 is 1. If C of C equal to 1. If C is not identically 0, there is an element vector x, so then Cx is 1. So take any such vector x, then I claim that phi must be phi x times C. Why? Because if I look at x minus phi x times x, no.
X minus psi x.
No, actually I have kernel of psi contain kernel of phi. So I should take
X minus.
okay, I should just say if Cx is not 0, that's enough. Then phi will be psi x times C. Why? Because you look at x minus psi x times C. Oh, no, I want Cx equal to 1, sorry. So I choose x as that psi x equal to 1. Then this belongs to, so psi of this is 0. So phi of this is also 0. That means phi of x must be psi x times psi x is just 1. So, no.
That means phi x equals to.
No, it must be phi x times psi x is 1, yeah, so what is this nonsense? C of this is 0, so phi of this is 0, phi of this is 0, but Cx is just 1. What is this x minus Cx times x? I'm saying something silly here. What does he say? Sorry. No, I want to say that what am I trying to say? See any x minus
Y minus psi x. You have put x and both x. Y minus psi x y. Psi of y minus psi x.
but psi x is 1, no? So why do we write psi x every time?
Fix x. Fix some x. Such that psi x equals to 1.
Okay.
Now you are going to prove that any y minus psi x y will be the content.
Why should I write psi x? Psi x is just 1. No. So what you must say is that no. Any y minus psi y x for any y, psi of y minus psi y times x is 0. Because psi x is 1. This is psi y minus psi y times psi x. That means phi of this is 0. Therefore, phi equal to phi of any y psi y times
psi of y phi. The constant time psi y.
phi of y is psi y times phi x.
So k
that is phi equal to phi x times psi. But anyway, the whole idea is that because the thing is co-dimensional, one, the kernel, if they have this, if you have inclusion of kernels, then it's completely determined by what it does on one vector. So that is basically the idea. So every phi is a multiple of psi. So going back to our proof, our phi was in psi-xf, in psi-ef. You wrote that phi as equal to summation phi I, and that summation phi I is nothing but summation phi I x times psi I. I should write xi times psi I, where psi I xi is 1. Anyway, the point is phi I is a multiple of psi I. And so the point is that this belongs to F. All the psi I's are in F and you just take a linear combination of those. And so you proved the necessary part. Now for the okay, let's try to rush to the other part. Okay, so what we want to say? We want to say phi is sigma E F continuous on E1 if and only phi and F bar. And this is the second session we had to prove. So first notice that if phi is sigma, see what is sigma EF? It is the smallest topology with respect to which all things in F are continuous. However, all things, by definition, F is contained in E star. That means the norm topology on E is one topology with respect to which everything in F is continuous. And so everything that is open in this topology, continuous in this topology, will be continuous in the norm topology. Right? Therefore, first you notice that F contained in E star implies that phi must also be in E star. Okay, so now I found a little, I think maybe there's a little mistake he's done or mistake I'm doing, but so in the very, I went through his proof and this, I seem to get something different. So, okay, so let us okay, so let us prove the easy part first. If phi is in F bar, that means it is the norm limit of things in F. And things in F are certainly continuous on, are certainly sigma EF continuous on all of V. And in particular, when you restrict to E1, there is sigma EF continuous there. And so this means you can find a sequence in F so that phi n converges to F in norm. So what does it mean to say that phi is in F bar? So by definition there exists sequence phi n in F star, phi n in F, such that norm phi n minus phi converges to 0. What does that mean? That means that phi n converges to phi uniformly on E1. That is the definition of norm convergence. But if phi n is certainly sigma EF continuous on E1, so uniform limit of continuous function is continuous, and so phi is also sigma EF continuous on E1. Okay, so let us go the non-trivial way. Okay, so phi is sigma EF continuous on E1. So what does that mean? Restricted to E1, it is continuous in this topology. So what does it mean to say it is continuous at 0? There is phi inverse of 1 should be an open set in this topology, restricted to E1. Right? So what does that mean? That means whenever I have, so what do basic open neighborhoods of 0 in this topology look like? They are going to be determined by finitely made semi-norms coming from this. So that means there exists C1, Cn in F such that, so what is the basic, so I want a basic neighborhood of 0 with respect to this topology in E1. That means I want to say there exists psi A such that x in E1 and summation absolute Cix less than some epsilon implies that absolute Px is less than 1. And that is the translation of continuity at 0 with respect to this topology. Correct? So what does that say? So I want to say, so let us look at any x in E. If x in E, look at and let's assume that x is not 0. I want to look at x divided by norm x plus summation p c a of x. That is summation mod Cax. So okay. So what can you say about this fellow? This has norm less than 1. If we call this y, then y is in norm y is less than or equal to 1 because new denominator is greater than or equal to norm x, and summation mod Ci of y will be the summation mod Ci of x divided by this quantity. This is a positive thing. Again, that will be less than or equal to that divided by this. Oh, I should have taken epsilon. Wait a minute. What should I take? Summation? Maybe I need to throw in an epsilon. Then what is mod Ci of y? Summation mod Ci of y. Is going to be summation mod Ci of x. That's why I have made in this book. Norm x plus. So I want less than epsilon. Maybe I want 1 over epsilon here. If I have 1 over epsilon there, then what would I have? Epsilon inverse summation mod Cix, which will be less than or equal to this over this, which will be epsilon. Right? That means y satisfies these conditions. So mod phi y is less than or equal to 1. What does that translate into if you kind of unravel all this messy denominators. That tells you that modulus of phi x divided by this is less than or equal to 1. So I can say this is less than or equal to norm x plus epsilon inverse summation mod Cix. No. No. So that is why. So it's saying this. Which is
You cannot have delta. Summation mod x less than for any epsilon. For any epsilon you can find delta. Delta you can choose one.
See, I'm saying that the phi inverse of the epsilon ball about 0 is a sigma x EF open subset of B of E1. And so, because F is closed under scalar multiplication, so I want to take phi inverse of the epsilon disk. I want to say if x is, so this is what an open, see, I don't have to throw in a scalar here because I can multiply the c's by scalars. F is a vector space. So a basic open neighborhood of 0 is going to look like this. So if I do this, then what then do I need this epsilon inverse? I can just do this, right? This is less than or equal to 1. So phi of this is less than or equal to epsilon. That means this is less than or equal to epsilon norm x plus epsilon summation mod psi x. Okay, so this is the thing. So in his book he has a norm phi rather than an epsilon here. See, what he says is, after writing down this condition, he says, hence we immediately infer that for any x in E, mod phi x less than or equal to epsilon norm x plus norm phi summation mod psi, he says. Whereas I seem to get that epsilon. Okay. So anyway, that is not going to be pertinent. See, what is pertinent is that now you can again appeal to that lemma of ours. Here phi is bounded by a sum of a certain bunch of seminorms. So I can write phi equal to phi 1 plus phi 2 where mod phi 1x is less than or equal to norm and mod phi 2, so less epsilon times norm, mod phi 2 less than or equal to epsilon summation mod Ci. Okay. But anyway, see, by the same argument as before, this will tell you that phi 2 is you can write this as a sum of things which are each of which is bounded by a multiple of peep Ci, epsilon peep Ci, and hence those things must actually be multiples of peep Ci, and so we find that phi 2 itself must be a linear combination of the Ci's. So we find that phi 2 must be in F. And what this says is norm of phi minus phi 2 is less than or equal to epsilon. Because this says that mod phi 1x less than or equal to epsilon norm x for all x. That means exactly that phi is approximable by things in F in the norm. Oh, it's already 110. Sorry about that. Okay, so this is the key funda. That the weak operator topology and the sigma weak topology. So I haven't yet proved that. So I should now prove that B of H is identifiable with the sigma E F bar continuous functionals on E. On B, E is B of H. I am saying B of H is identifiable with the sigma B of H F bar continuous functionals on B of H. That's what we have to see. And then we will have what we want. Okay.